Metal Organic Frameworks in Dentistry. Porous Chemistry at the Oral Frontier, Mechanisms, Translation, and Next Steps by AZLAN ADNAN, M.A. Saturday, 3rd January 2026. Introduction: A New Material Dimension for Oral Health. Metal organic frameworks, MOFs, are engineered, crystalline materials composed of metal ions coordinated with organic linkers, forming structures with tunable pore size, ultra-high surface area, and adjustable chemistry. Originally explored for gas storage and catalysis, MOFs increasingly attract interest in biomedicine, including dental science. MOFs were recognized in the 2025 Nobel Prize in Chemistry for enabling designers to create new rooms for chemistry, making them compelling candidates for dental materials that do more than fill space. They interact with biological and microbial environments. Dentistry's core challenges, caries, adhesive failure, infection, and tissue regeneration, are all, at root, problems of control and response at microscopic interfaces. As of early 2026, MOF research in dentistry remains largely preclinical, with a small number of pilot human studies, notably a 2025 Shofu Osaka University pediatric trial, illustrating early translational movement. This article summarizes current evidence, mechanisms, and realistic horizons for clinical application. 1. Antibacterial and remineralizing caries solutions, mechanisms, and pilots. Caries involves bacterial biofilms producing acids that demineralize enamel and dentin. MOFs can tackle this via ion release and structural reinforcement. Mechanism: silver-loaded MOFs, e.g. AMOF5, incorporated into composite matrices, act as slow-release reservoirs for AGB, CuPis, or Z-N-port-Bi ions. These ions disrupt bacterial membranes and enzyme systems, reducing Streptococcus mutans viability. Moreover, the porosity allows sustained fluoride and metal ion delivery deeper into dentin. Evidence: a 2025 scientific report study showed A@MOF composites promoted dentin remineralization at levels comparable to 38% silver diamine fluoride (SDF) without the characteristic staining. Treated dentinal tubules exhibited more effective occlusion, and intertubular collagen density was higher versus controls. Translation: in late 2025, a small pediatric clinical pilot, Shofu Osaka University, evaluated a MOF-enhanced glass ionomer cement in elementary school restorations for safety and early antibacterial effect. Initial results: N40 restorations, 6-month follow-up, reported no adverse effects and preliminary reductions in secondary caries incidence compared with matched controls. This pilot supports feasibility but requires larger, multi-center trials before adoption. 2. Enhanced restorative materials, multifaceted mechanical benefits. Restorative composites and adhesives face challenges in mechanical durability, water sorption, and bond stability. Mechanism: MOFs introduce high surface area fillers with tailorable chemistry. Zirconium-based MOFs like UIO66NH2 improve flexural strength, elastic modulus, and reduce water uptake, mitigating hydrolytic degradation, a major cause of microleakage. Evidence: studies incorporating UIO66-type frameworks into resin composites observed significantly higher mechanical properties versus silica controls. A 2026 study of a strontium-based MOF in experimental adhesive systems reported enhanced microtensile bond strength, reduced nanoleakage, and increased apatite nucleation under simulated oral conditions. Cytocompatibility assays, ISO 10993 series, showed no significant cytotoxicity at functional concentrations. Translation: these mechanical and bioactive enhancements position MOFs as functional fillers rather than passive particulates. However, clinical validation of long-term performance under cyclic loading and thermal stress, typical of oral environments, is still needed. 3. Protecting collagen, bond interface stability. Adhesive bond degradation at the dentin interface is driven by water infiltration and proteolytic collagen breakdown. Mechanism: ZN-based zeolitic imidazolate frameworks, ZIF-8, can be grown in situ on demineralized collagen to form a protective nanolayer, inhibiting matrix metalloproteinases, MMPs, implicated in bond degradation. This structural reinforcement may slow collagen collapse and sustain bond integrity. Evidence: ex vivo dentin models show that ZIF-8 treated collagen exhibits reduced MMP activity and improved mechanical resilience, suggesting a potential route to more durable bonds without altering adhesive chemistry fundamentally. Translation: current data are in vitro ex vivo, Translation to clinical adhesive systems awaits formulation into commercially feasible primers or conditioning agents. HADRA 4. Periodontal and implant applications. Targeted delivery. Periodontal disease and periimplantitis are biofilm-driven inflammatory conditions requiring targeted antimicrobial and regenerative strategies. Mechanism and evidence. MOF-loaded hydrogels, e.g. AG-MOF with an alginate matrices, demonstrate broad antibacterial activity, biofilm inhibition, and enhanced endothelial responses in preclinical periodontitis models. Similarly, MOF polymer composites are being engineered to deliver anti-inflammatory drugs or osteoinductive ions, Mg-quersbys, Ca-quersbys, across periodontal defects, promoting both antimicrobial and regenerative environments. Quantified outcomes in rodent models include higher bone fill and reduced inflammatory markers compared with controls. Translation. These systems reveal two clinical pathways: localized drug delivery from implant coatings or gels, mitigating infection without systemic antibiotics. MOF-enhanced scaffolds supporting guided tissue regeneration, GTR, and alveolar bone repair post-periodontal surgery. SCHNAR 5. Safety, finite scales, and regulatory pathways. Biocompatibility. MOFs' ion release profiles influence both efficacy and safety. Reviews of MOF biomedical applications stress that degradation products, ion flux, and local pH effects must be quantified under conditions mimicking oral fluids and bacterial biofilms. Manufacturability. Many MOF syntheses, solvothermal, microemulsion, are suited to laboratory scales. Industrial adaptation, batch control, reproducibility, regulatory quality systems remains an active materials engineering challenge. Regulatory environment. Agency pathways, FDA, EMA, require not just preclinical toxicology and performance data, but evidence of long-term stability in the dynamic oral environment, chewing, temperature swings, saliva enzymes, and microbial ecosystems. HAMP 6 current status. Reality check. January 2026. Lab research is robust. Numerous peer-reviewed studies confirm MOF's antimicrobial, mechanical, and matrix protective potential. Preclinical models are expanding. Animal and simulated oral environments show benefits for periodontal and bone contexts. Early pilots exist. Notably, a 2025 pediatric MOF glass ionomer trial in Japan demonstrated safety and early antibacterial effects. Clinical translation lags. No universally approved MOF-enhanced dental products are marketed globally. Regulatory review is ongoing. Conclusion. Looking into the pores of dental future MOFs are not panaceas. They are a distinct category of dental biomaterial that can be engineered to address specific limitations of current therapies: sustained antimicrobial release, reinforcement of adhesive bonds, adaptive material properties, and localized drug delivery. Dentistry in 2026 sits at a proof-of-concept crossroads. Within the next 5 years, clinicians may encounter emerging MOF inside materials in select restorative, periodontal, and surgical contexts, where controlled chemistry meets clinical need. They will not replace amalgam or conventional composites tomorrow, but the pores they leave behind may enable treatments that are simultaneously smarter, stronger, and biologically attentive. Key references. Learn to cook with confidence. A holiday cooking experience for teens and school leavers. Cooking is one of the most important life skills a young person can develop. We eat every day, and knowing how to prepare good food sets you up for independence, creativity, and lifelong well-being. In my holiday cooking classes, I go far beyond teaching recipes. I blend knife skills with the wonders of food science, the chemistry, biochemistry, and nutrition that shape every flavor, texture, and aroma. It's the practical, delicious side of the science you learn at school. My sessions are fully hands-on. You will feel the warmth rising from a pan, hear onions sizzling into sweetness, smell butter turning nutty and golden, and watch simple ingredients transform into something extraordinary. Cooking becomes a sensory adventure, not a chore. To ensure every student gets dedicated attention, I keep each class small, just 3 to 6 participants. We learn by doing. We taste constantly. We experiment with confidence, and we uncover why small changes in technique make big differences on the plate. Classes are held by appointment throughout the December school holidays. Each session gently builds confidence, skill, and curiosity as students work from raw ingredients to a finished dish they can proudly serve at home. And here's something parents love. My class fees are by donation. If your child walks away bored or unmoved, you pay nothing. But if your child returns home excited, inspired, and perhaps presents you with a classic French onion soup, richly caramelized and impossibly fragrant, then simply contribute what you think that experience is worth. If your child keeps pestering you to bring them back for more classes, well, you'll know you've got your money's worth. All proceeds help fund my ongoing eye treatments, so every contribution goes to good use. Students will also learn how to choose fresh ingredients and shop smart. Do give them some grocery money, because selecting produce confidently is just as important as cooking it well. If you're ready to turn curiosity into skill and skill into joy, I would love to welcome your teen into my kitchen. Parents are most welcome to sit in as chaperones or return at the end to savor their children's culinary creations.